All right, so as I was saying, we're going to look at elastic potential energy, which is the energy stored by a spring. And so the first thing we have here is what's called Hooke's law, which is the magnitude of the force, elastic force, that's a little Fe there, you can't see it, exerted by the spring is directly proportional to the distance the spring has moved from its rest position, which I think most of us know is if you've ever dealt with a spring, is that if you pull it back farther, it pulls back on you farther. Or if you push it in farther, it pushes back on you further. All right, so I think some of that is natural. And so again, well, let's see here, I'm going to write it Fe. So I want to write that a little bit better. Again, is equal to what is called our elastic force. All right, now there's there's kind of two formulas, sort of really one, because we're looking at the magnitude of our elastic force. It's Fe is equal to K times X. All right, now what is X or what is K? Well, this is where K is the force constant. So that's how strong your spring is. The units are measured in newtons per meter. So how much force per unit of you moving it or compressing it or stretching it. And X, let's see here, I'm going to throw that in here. X is the distance from the rest position. So you can have two ways, like I said, that a spring can work. You can compress a spring or you can stretch the spring. But either way, X is the distance from that rest position, which would be our dotted line here on my diagram. Now, again, this formula can be written a little bit differently as a vector because we're dealing with forces. And so what we have is F, again, our elastic force, vector symbol, with negative K times, again, X, but X is a vector. And the only difference here is that the negative sign, how am I going to say this? I'll type it in. The negative sign is because Fe, our elastic force, and X are in the opposite direction. What I mean by that is that in my diagram, if I look here and I compress the spring, so I move the spring to the left, well, that spring is going to push to the right. If I stretch the spring to the right, the spring is going to pull back to the left. So that's all that matters. So this formula is very rarely used because it's intuitively known that, hey, listen, if you compress the spring, it'll push back on you. If you stretch it, it'll pull back on you. So it's all Fe and X are always in the opposite direction. Yeah, so there's our symbol there. Whoops, it's that picture. I won't go on. So there we go. So here's an example of that. I wish I had had that before. So there's an example of our stretch is positive. Again, you can see that the force and the X value are in the opposite direction. Now, another thing that we're going to look at is the elastic potential energy, because again, this unit, we're all about energy, right? And so our elastic potential energy, so I'll throw that down there, label it, elastic potential energy. And that again is the energy that is stored in the spring, because when you compress it, it wants to, it wants to stretch back out. And when you stretch it, it wants to compress backwards. Well, your elastic potential energy is equal to 1/2 K, which again is our force constant, X squared. So again, familiar values. All right, so we have our two formulas, because again, the vector formula for the other is not often used. All right, so there it is. All right, so let's try out some questions here. Actually, I think I just have one big question, multiple parts. All right, so this is kind of like a bungee cord kind of an example. An 80 kilogram person uses a 25-meter long spring cord, bungee cord, to jump off a bridge. When the person jumps and falls, they eventually become stopped 150 meters below the bridge. What is the force constant of the spring? And so what we're looking for here is the force constant. That's our K value we're looking for here. All right, now I'm going to draw a little bit of a picture here of what we've got going on. Here's my bridge. All right, the string, or the bungee cord, if you will, hangs down. It hangs down. It's 25 meters long. Now, this person jumps, or, I guess jumps, and this bungee cord expands all the way down. And then it hits right in here. Whoops. Where it gets this far down. And this is now 150 meters below the bridge. Okay. All right, so there's where we started. Now we hang down to 150 meters. Let's see here. So that's 150 meters all the way down. All right, so what we're looking for is the force constant of the spring. Now, here's a key, is that if I'm at the very bottom here, I should have left myself a little bit more room. Let's see if I can move this. Yeah, I can move that. Let's see here. Oops. All right, so now I'm going to move this person out a bit, and they're right here. All right, so now the key here is that they are stopped below the bridge. So here's what's happening is this spring, because it's stretched, is pulling up on the person, their FE. But because they're stopped, the net force is 0. What is the only force acting on this person as they're suspended in midair? It is the force of gravity. All right, so in this case, at this point, not all the time, but at this point, FE is equal to FG. All right, and so I can figure out what our force of gravity is because we have the mass of the person. So FG, once again, is M times G, which in this case is, this person is 80 kilograms. And of course, we're on Earth, so it's 9.8 meters per second. I multiply those two numbers, and let's see here. What do I end up with? I won't do space. That's cool. We get, now 80 times 9.8. I get round number, 784 newtons. All right, so here's the key, is we want K. Well, I'm going to use my formula, the fact that our elastic force is equal to K times X. All right, now, I know FE. It's equal to 784 newtons. I want my K, right? That's what we want. I need to know how far the spring has been extended. Well, look at this. It goes 150 meters below the bridge. It's already 25 meters long, so the X value here is the difference. And so the X value is 125. Because its rest position, it naturally hangs 25 meters below the bridge. And so it's stretching another 125 to get to 150. So the stretch is 150. All right, so now I can substitute that in, is that I know again that because of gravity and the elastic force of my bungee cord are balanced out, that it's 784. The K value I'm trying to find, the extension, is 125 meters. Again, needs to be in our standard units. All right, and then I'm going to divide both sides by 125 to get my K value. And in this case, I take 784, I divide it by 125, and I'm getting 6.27 newtons per meter. So that's how strong this spring is, this bungee cord. It applies 6.27 newtons for every meter that it has been extended or compressed. Works both ways. All right. Oh, different situation now. Gonna have to keep moving these. Oops. All right. So now we're looking at what is the net force of the person when they are 100 meters below the bridge. So we're up in here now. little bit of a different situation. And so again, I'm going to draw a free body diagram here. So we want to know the net force. And again, when this person is hanging on the bungee cord, they still have that force of gravity acting on them, right? That's not changing. And that, I believe, again, is 784 newtons. We have the elastic force, which is pushing up. I don't know what it is yet. Now, again, we're looking for the net force. And of course, the net force is add up all our forces. So we have the net force is equal to Fe pulling up, Fg, of course, pulling down. All right. So I'm looking for my net force. I already got Fg, so I need to find Fe. Well, I can find Fe because I have all the values, because again, Fe, our elastic force, is equal to K times X. I know K is 6.27. Now on this bridge, it is hanging down 25 meters, but then we're looking at this thing extending down all the way 100 meters below the bridge, 100 total. So our extension is going to be, well, 100 minus 25. So it's actually at this point only extended 75 meters. All right, so I'm going to plug those values in. All right, so the elastic force that's being applied is going to be 6.27. That's our spring constant times our force constant of our spring, and times 75. All right, I multiply those two numbers, and 6.27 times 75 is 470.25 newtons. There we go. All right, so now I can find my net force. And so the net force, because I have my Fe, I've got my Fg. Well, let's see here. So I've got my F net is equal to Fe, which is my 470.25 newtons, subtract my force of gravity, which is 784 newtons. And so my net force at this moment is going to be negative 313.75 newtons. Or, again, looking at it as a vector, it's 313.75 newtons, but it is negative, and so that means it is directed down. And that is why this person keeps falling, because the net force, gravity, is still winning. The spring is not strong enough yet to balance things out, like in their A here. All right, so we're still moving down. And in fact, what we can find out is determine the acceleration of the person. So how fast are they getting? How much are they getting faster at this point? How fast are they accelerating? Now, if you just jump off a bridge, and I obviously suggest don't do that, you would just fall down at your acceleration would be 9.8 meters per second. But we have this spring helping us out, pulling it up a bit. All right, now at 100 meters below the bridge, here's what we do know. At this point, we know that our net force is equal to 313.75 newtons, well down. All right, we know the mass of this person at this point, which is 80 kilograms. And of course, we're looking for the acceleration. And lo and behold, we're in our forces unit here, or just coming off our forces unit here. Well, we have Newton's second law, F equals ma. All right, and so, well, I'm going to take into account my direction right off the bat with my force. So I'll put negative 313.75, because again, negative, it's down. Our mass is 80, and I'm trying to find my acceleration. All right, so I'm going to divide both sides by 80. And as you can see, I'm clearly going to get a negative answer here, which means my acceleration is down, which makes sense because I just jumped off a bridge with a bungee cord. I'm still accelerating downwards. And so the answer is going to be negative 3.92 meters per second squared. But because it's negative, I realize all that means is that I'm still accelerating downwards. Not at the same rate as if I jumped off with no jump bungee cord, but it's still accelerating downwards. All right, last one. What is the elastic potential energy in the spring when the person is 100 meters below the bridge? So what energy do they hold? Again, I have my formula for elastic potential energy that we're going to look at a little bit more here at 11 o'clock, but is equal to 1/2 kx squared. And in fact, we already have all these values. We have k. We know our spring constant is 6.27. And at 100 meters below the bridge, our x is 75. All right, so I'm going to plug those two values in. And let's see here. We get EE, our elastic potential energy. Again, I always like to convert a fraction to a number, in this case a decimal. My spring constant is 6.27. And my x value, we get 75. And it is squared. All right. Oh, yeah, there we go. Okay. And again, I got to follow Bedmas. All right. So I'm just going to go by 0.5 times my 6.27 times, again, I got to follow Bedmas here. So go 75 squared. I still see that in grade 12. People don't follow Bedmas. So I get 5,625. All right. And then lastly, I get to multiply those three numbers and again go to two decimal places. I get 17,634.38. And because again we're talking about energy, we are looking at joules. All right, so this elastic potential energy, that is something we are going to look at a little bit closer, like I said, in our next lesson, where we look at the interaction of springs and basically being shot from a spring and looking at how fast you would go, that kind of stuff. All right, so that is